So on the underside, we have type 2 hypervisors, which are hypervisors that need the presence of an existing operating system in order to rely on it for its virtualization routines. So as an example, we can name the Linux KVM. So on my thesis, I was focused on type 1 hypervisors. So most type 1 hypervisors, in order to reduce their trusted computing base and to benefit from all operating system functionalities, they are going to rely on a particular virtual machine which will have more privileges than the others. So this virtual machine, I will note it the PVM, is going to be responsible to carry out management operations such as virtual machine creation, migration, checkpointing, for example. Depending on the type of virtualization used, it will be also responsible to provide or to do IO device multiplexing for all the other virtual machines. And it will also host the monitoring tools such as the Nova Compute component if you are using the OpenStack data center management framework. So depending on the hypervisor you are using, this component is going to have a different name. On the Zen hypervisor, it will be named the domain 0, so DOM 0. And in the Hyper-V hypervisor, it will be named the parent partition. So this architecture based on the particular on the privileged virtual machine has several advantages, but when using it, you are faced with two main challenges. So these challenges are the resource management of the privileged virtual machine and the fault tolerance of the later component. For the resource management, the question boils down to how to efficiently provision resources for the privileged virtual machine. And this question has several subparts. The first one is the provisioning in terms of CPU and memory. And the CPU and memory of the privileged virtual machine has impacts on several activities such as the virtual machine's IO applications. So to show this impact, we carry out a simple experiment where we provided fixed resources to the privileged virtual machine. Inside the target virtual machine, we installed the WordPress application Magento, and we were interested in monitoring its throughput. And step by step, we start the virtual machines that are going to run a network intensive application, so TGN here. And during the experiment, we are interested in measuring the load on the resources of the privileged virtual machine and the throughput of the WordPress application in our target virtual machine as the number of collocated virtual machine increases. So what we can observe on the top figure is that as we increase the number of collocated virtual machines, the load on the resources of the privileged virtual machine increases. And on the other side, so on the left top figure, on the right top figure, we can see that as a result, the throughput of the WordPress application also decreases as we increase the number of collocated virtual machines. So when we had this result, we thought it may be the network card that is being a bottleneck. So to confirm that the bottleneck here was the resources of the privileged virtual machine, we repeated the same experiment where we provided more resources to the privileged virtual machine. And what we observe on the bottom figures is that the rate at which the load increases on the resources of the privileged virtual machine is slower, and as a result, the throughput in the target WordPress application is quite stable. So CPU and memory of the privileged virtual machine also affects administrative operations such as virtual machine creation and migration time, which are crucial operations for scalability or even a maintenance operation. So here we plot the migration and the creation time against the load on the resources of the privileged virtual machine, and we can observe that as the load on the resources of the privileged virtual machine increases, the time needed to create and migrate is also increasing. The second subpart of this question is in terms of NUMA placement, because on non-uniform memory architectures, the distance between the CPU and the memory is going to affect the computing time. So aside from provisioning resources, we must also know where should these resources be placed. So to show the impact, we run an IO application inside the virtual machine in two situations where the resources of the privileged virtual machine are collocated with that of our target VM, collocated means here on the same NUMA node, and another situation where the resources are not collocated. So we can see that we have a better latency, so lower latency, and a better throughput, so higher throughput, when the resources of the privileged virtual machine are collocated with that of the virtual machine. The last subpart of this provisioning issue is in terms of billing. So since the privileged virtual machine needs resources, who should pay for these resources? So who should be charged for this? Is it the cloud provider, so is it the virtualization system, or is it the client that must be charged for these resources? And how should we even charge this? For the second challenge, since the privileged virtual machine has a crucial role in the virtualized infrastructure, it represents a single point of failure because a crash happening in the privileged virtual machine is going to trigger the impossibility to connect to the physical server, so no monitoring possibilities, no possibility to manage your virtual machine, so no possibility to create, migrate, or even shut down. And for IO applications running inside virtual machine, they will just stop. So during this presentation, I'm going to take each challenge and try to present what are the existing solutions, what we propose, and the evaluations results we obtain. So let's start with the first challenge, which is the privileged virtual machine resource management. So there are several approaches that exist, such as Oracle VM server that propose a formula to determine the memory allocation needed by the privileged virtual machine. But this kind of static approach either leads to under provisioning, which means that the privileged virtual machine will be in a situation where it lacks resources to provide to function correctly, or over provisioning, which means that the privileged virtual machine will be wasting resources that will be used to create other virtual machines in order to increase the consolidation rate. In the research, there are other techniques that tries to compute the CPU time used by the privileged virtual machine for user virtual machines, and there are even ideas that try to push the idea forward to compute the CPU time and charge it on the virtual machine by trying to adjust their scheduling with. However, most of these approaches either propose static solutions or they do not correctly handle NUMA architectures. So this is a real problem because in the privileged virtual machine, what runs are standard operating systems, such as powered by the standard kernel, such as the Linux kernel, where the resource management manager do not take into account the particularity of the privileged virtual machine, which is its correlation with the activities of the virtual machine that are running on the systems. So to mitigate this, we propose what we call closure, which is a design principle that enforces, which is a design principle to build an operating system for the privileged virtual machine that enforces through three rules. The first one is the on-demand, which states that the resources for the privileged virtual machine should be allocated depending on the needs of the virtualized systems. The pay-per-use rule, which states that each time the privileged virtual machine should use resources for target virtual machine, that virtual machine should be charged for the resources used. And the last rule is the locality, which states that each time the privileged virtual machine should use resources for target virtual machine, it should use resources which are close as possible, that means on the same NUMA node to that of the target virtual machine. So concretely, how does it reflect compared to the standard model where the privileged virtual machine had fixed resources, memory and CPU? Here we consider the privileged virtual machine as two different entities. The first entity, which we name the main container, will be exclusively reserved for administrative tasks that have nothing to do with the virtual machine, so nothing to do with the activities of the virtual machine, and a secondary container which is reserved for the operations of the privileged virtual machine for that targets the running virtual machines. So the secondary container is going to use resources of the target virtual machines, and by doing so we are going to charge the target virtual machine, and we are going to benefit from locality. So concretely, for the main container resource management, since it is responsible for activities that do not vary with the load imposed by virtual machine, we can do a static calibration for its resources. And to prove that, we took three well-known data center management framework: OpenStack, OpenNebula, and Eucalyptus. And we showed that with fixed resources, it can provide good performance. For the secondary resource management, we use a simple algorithm that states that at boot of the machine, the secondary container will have as many vCPUs, so virtual CPUs, as CPU on the system after we exclude the one reserved for the main container, and each vCPU will be mapped to one CPU. And for each task of the secondary container that needs to be scheduled to perform work for a target virtual machine, what we are going to do, we are going to pick a CPU where the target virtual machine is running and schedule that task on one of those CPU. So by doing so, we are charging, so we are taking CPU time from on the target virtual machine, and we are also benefiting from node locality because we are going to run on the same node as that of the target virtual machine. So how does it reflect? I'm going to present here just the case for the network reception. So by default, what happens when a packet arrives on the network card is the packet is placed in a queue at the step R1 at step R0 here, and there's an interrupt which is generated. The interrupt is then transmitted via I/O API to a physical CPU. Then there's a virtual interrupt at step R2 that is sent to a virtual CPU of the privileged virtual machine. Then the virtual interrupt handler, so the event channel handler, is going to be triggered. And what happens is that it is divided into two parts. There's a bottom half that is going to mask interrupts arriving on the network card, and then it is going to schedule a soft EIQ, which is going to trigger the processing of the different of the packet. So at this step, the soft EIQ is triggered, and what happens is that it is just going for each packet to copy it from the network queue to from the network queue here to the socket buffer structure, then flow through the IP stack up to the bridge. Then at the bridge level, we can identify via the packet headers where should the packet be routed to, on which backend, which is the representative of the fake driver inside to the target virtual machine. So once the backend is identified, you can now start the process of sending the packet information to the target virtual machine. So how do we apply closure? For the first step for R1, where we notify physical CPU of the interrupt, we do not want the main container vCPU to treat this interrupt. So what we do, we use EIQ balance in order to balance the interrupts arriving on the network card between the vCPUs of the secondary container. So by doing so, we are leaving out the main container vCPU so that it should be solely reserved for administrative operation. So at step R2, since we need to notify the privileged virtual machine vCPU, what we do is that we implement what we call hyperload balancing, which consists of choosing a vCPU of the secondary container, which is mapped to one CPU of a privileged virtual machine based on the network or based on the I/O activities. So what it means is that more a virtual machine will do I/O activities, more we are going to schedule the event channel here on one of its CPU. At step R4, since there's the soft EIQ that is scheduled and that needs to process the packet information and send to the target virtual machine, what we want is that this processing should be done on the CPU, on the virtual CPU, which is close as that of the virtual machine. So what we did is to identify the target virtual machine at this step here using a simple hash mechanism where each virtual machine has a hash which is sent in each packet at the exterior, and when it comes back at this step, we can happily identify the target virtual machine. So when we identify a target virtual machine, we can now know on which vCPU we can schedule all the backend processing for the secondary container. So this technique matches perfectly with the old API model where one interrupt corresponded to one packet treatment. But for the new API model where an interrupt corresponds to one packet, then there will be polling for the rest of the packet arriving. We had to modify the network driver in order to identify for each packet to process the target virtual machine. So we prototype closer using the Zen 4.7 and Linux kernel 4.10.3, and we were interested in seeing the improvement in terms of I/O performance of virtual machine, the improvement in administrative tasks, and the fairness regarding resource usage. So to measure the improvement for network packet reception emission, we did an experiment where inside the virtual machine we run netperf with different packet size and constant load, and we observed that we improve with our mechanism network reception and emission by 36 and 42% respectively, and most of the gain comes from the backend that is doing all its processing on the same NUMA node as that of the target virtual machine. We were also interested in seeing how good we are able to identify the virtual CPU where should be routed the packet. So we did the situation where we have the two virtual machines that are running NetBev, and we were interested in seeing how good we are able to identify the target virtual machine. So we compared three approaches. So the whole API model, which corresponds to one interrupt, corresponds to one packet. The NAPI-N, where there's the interrupt polling, and for each packet in the polling, we identify the target virtual machine. And NAPI-1, where is the default model where there's an interrupt. We identify the destination for the first packet, and then the remaining packet which will be polled will be sent to the destination which has been identified for the first one. So we can see that with OAPI and NAPI-N, this one and this one, we have good performance, and the error rate is low. But for NAPI-1, the performance improvement is lower, and the error rate is higher because we do not identify correctly for each packet which is processed. We are also able to improve migration operation by up to 33%. This is mostly due to the iterative copy phase, which is done on each node where the memory which is copied is done. We are also interested in fairness and to see if the main container resources were left out of all the I/O processing. So we did an experiment where we had three virtual machines imposing a certain load, 1,000 requests per second, 3,000 and 6,000. So this corresponds to 10%, 30%, and 6,000 and 60%. And what we were interested in seeing the contribution to the I/O processing. And we can see that with with OAPI and NAPI-N, we have contribution which are almost equal to what is expected, so 10, 30, and 60. However, for NAPI-1, what we observe is that the contribution are not really equal to what we expected, because there's a kind of prediction for the destination of each packet which is processed. But however, independent of the solution we are using, we can see that compared to the vanilla implementation of the Zen hypervisor, the load imposed on the main container is low, so it did not vary with the activities of the virtual machines. So to summarize this, we propose a closer design principle for building an operating system for the privileged virtual machine that enforces three rules: on demand, pay per use, and locality. The prototype we build shows that we can achieve good resource provisioning while improving both the I/O application inside virtual machines and administrative tasks. However, when we were carrying out our experiment, we discovered an issue regarding the placement of the resources of the memory of the privileged virtual machine on NUMA architectures, and the technique which is used to transfer information between the backend and the front end inside the virtual machine, which is known as zero copy, which consists in memory page flipping. So let's summarize rapidly what is zero copy. So we're in a situation where inside the privileged virtual machine, we have in the memory space of the privileged virtual machine, we have a packet information that is destined to one virtual machine. So instead of copying from the memory space of the privileged virtual machine to the memory space of the virtual machine, what the hypervisors do is that it's going to ask the virtual machine destination a set of free pages. It's going to obtain the grants on those pages. So grants here are write accesses. Do the same for the pages that contains the virtual machine information inside the privileged virtual machine. It's going then to exchange these grants and map them on each memory space. So by doing so, the privileged virtual machine will have some free pages, and the virtual machine will now have access to the pages containing its information. So this provides better throughput than the standard memory copy, and it works well in uniform memory architectures. However, on non-uniform memory architectures, since the trend is to allocate all the resources of the privileged virtual machine on a NUMA node which will be distant to that of the remaining virtual machines, repeated network I/O operations is going to make the privileged virtual machine have memory on the other nodes, and the virtual machines are going to have memory on the node of the privileged virtual machine. So this is going to disrupt the memory topology, and the virtual machine will not be informed of that, and we will have scheduling and memory allocation policies which will be optimized for the wrong topology. So to show this problem, what we did is to execute inside the virtual machine an intensive network application, collaborative filtering from the big database suite. The virtual machine had 16 gigabytes on a NUMA node, and the previous virtual machine had 8 gigabytes on a different NUMA node. And during all the experiment, we were interested in measuring the virtual machine memory percentage on each node. And what we observe is that at the end of the experiment, up to 22% of the memory has become remote without the virtual machine being aware of that. And as a result, memory sensitive applications such as stream can be affected. Here we plot the performance of the throughput of the stream benchmark memory throughput before running the intensive network application in our target virtual machine, and after running the network intensive application, and we can see there is a difference in the memory throughput of up to 13%. So to correct this, we propose two approaches. The first one is to have a dedicated page pool, and the second one is to have to perform asynchronous memory migration. For the dedicated page pool, it consists of having a pool of pages inside the target virtual machine, which will be exclusively reserved for zero copy or memory flipping operation. So what we are going to do, each time we need free pages to send to the privileged virtual machine, we are going to pick one of the pages inside the pool, and we are also going to mark all the pages that we obtained from the privileged virtual machine, which can be potentially remote. And the idea here is to block the access. So other applications inside the virtual machine will not allocate pages inside our pool. So here we need to know what is the correct sizing policy for this pool. So either we use a static pool size. This can be fastidious and will not evolve depending on the load of the network application inside the virtual machine. So we propose a dynamic solution for the sizing of the pool that monitors the percentage usage of the pages inside the pool. So each time the percentage use exceeds the 90%, we are going to increase the size of the pool by 10%. And each time it decreases below 20%, we are going to remove 10% of the pool size. So by doing so, we can have a pool size which will adjust to the activities or to the load of the virtual machine. So the second approach is to have asynchronous memory migration, which is quite straightforward. It consists in asynchronously migrate all the pages that became remote due to zero copy. And here the migration can be triggered either on a periodic basis, either based on the amount of memory that has become remote. So we prototype this on Zen 4.9 using the Linux kernel 4.14.2, and we were interested in doing our evaluations to measure, to see if you can effectively control the amount of memory that becomes remote, and to measure the side effects on memory sensitive applications. So here what we observe is that here we run the same experiment as before, that consists of running the network intensive application from big database. And we can see that compared to the default zero copy here, with the dedicated page pool and the periodic asynchronous migration, we can control, so the amount of memory that becomes remote is under control. We can control it, and as a result, memory sensitive applications such as stream and a link bench provide better result after running the network intensive application. So here we can see that for the default approach, the gap between the first and the second one is quite high, but with our solution we can maintain the performance between the two runs. So for this issue, we propose a dedicated page pool approach and to have asynchronous memory migration. The prototype we build shows that we can effectively control the amount of memory that becomes remote while preserving the performance of memory sensitive application and continue to benefit from zero copy. So after this, we went to the fault tolerance problem of the privileged virtual machines. So there are some techniques or some approaches that try to propose something to this. The first one is full replication that is used by some data centers such as some cloud providers such as Nutanix that consists of replicating the components of the privileged virtual machine across the data center. But for obvious reasons, this is resource consuming and imposes a high load to maintain synchronous state across the different replicas in the data center. There's another approach which has been done to mitigate the security issues, which consists in breaking the privileged virtual machine into smaller blocks or into independent blocks, and for each block perform periodic reboot in order to recover from a faulted state that can happen if the component is corrupted or even the component crashed. So this effectively reduces some security flaws, but you cannot use it constantly because it introduces a huge overhead for latency sensitive applications. And to show the impact of the reboot, we perform a benchmark where we run inside the virtual machine applications from the tailbench suite, which are latency sensitive, while rebooting the component responsible to provide the network access to the virtual machines. And what we observe is that we have up to 2,000 times latencies for the 2,000 times in the condition for the main latencies, 1,300 and 1,200 for the 95 and 99 percentiles. So to mitigate this, to propose solution to this, we propose what we call PPVMM for Phoenix PVMVMM, which relies on three design principles. The first one is disaggregation that has been presented before, that consists in splitting the privileged virtual machine into independent blocks. The second one is specialization, that consists of having specialized fault detection and recovery techniques for each block. And the last one is proactivity, that consists in triggering recovery mechanisms as soon as the fault occurs. So we apply this on the Zen hypervisor, and what happens is that it results in the privileged virtual machine being decomposed into four submodules that run each in a dedicated unique kernel. And these blocks, we categorize them into two groups: stateful components, the Zen Store UK, XS UK, that stores information about the running virtual machine and the system, and this information can be queried by the hypervisor and the other virtual machines. The other group are stateless blocks, such as the Net UK, that provides network access to the virtual machine, This UK, that provides block device access to virtual machine, and Tool UK, that hosts the Zen tool stack, which is the administration data plane. So for stateless component, we try to monitor in order to detect if there is an unavailability of the component. We monitor heartbeats using a component in the hypervisor that is going to detect if there is a problem, and via a decision maker module, we're going to trigger the recovery dedicated for that component. So here we assume that the hypervisor is reliable via existing techniques such as rehype or even hypervisor recovery without reboot presented in the SN 2018. So due to time constraint, here we just present the techniques we use to detect and correct fault for the Zen Store and the Net UK. For the Zen Store UK, so XS UK, since it is a stateful component, we must prevail against two things: the unavailability that can happen due to a lack of resources or crash, and database it hosts corruption due to hardware faults such as bit fiddle. So for the unavailability, since the memory footprint of the Zen Store is quite small, what we do is we maintain replicas of the Zen Store on the same server, and to ensure a consensus between all these replicas, we introduce a TCD that is going to, for each incoming request to the Zen Store, is going to send the request to one particular Zen Store. Then after the processing is done, it's going to broadcast the request to the remaining Zen Store, so to ensure synchronous state between all the replicas. And if there is a Zen Store that undergoes a crash or is now unavailable, a TCD will transparently handle this by routing requests to other Zen Store and inform the hypervisor to trigger the recovery, which is just the reboot of the replica. For database corruption, since the Zen Store is FS-like structure, so with directories. If there is a write on a corrupted directory, there's no problem because it's going to override the corrupted information. So the real issue here is for read request. So what happens for read request is that for the selected Zen store that has been chosen to compute the request, we are going to compute the hash of the database of that Zen store and compare it with a hash that is constantly maintained in the hypervisor. And if the two mismatches, we can detect that there has been a problem, and now we will send the request to another Zen store while triggering the recovery of this faulty Zen store. So the recovery consisting of replaying logs of request in order to obtain the same Zen store. For the net UK, aside from the unavailability, for the unavailability problem, it can happen at two levels. Either it is the entire net UK that has undergone the problem, or since the network driver is generally a faulty component, it can be the network driver that undergoes a fault. So to detect this, we rely on timeouts and we combine the technique as an existing technique known as shadow driver. So concretely, what happens is that when the network driver starts its processing, which is divided into two parts, the top half and the bottom half. Once the top half schedules the bottom half, is going to inform the hypervisor, and the hypervisor will note the time t0. And once if after t0 plus a certain t max, the network driver or the bottom half processing has not yet informed the hypervisor that, okay, I finished my processing, we can detect that there is a problem with the network driver. And what happens is that we are going to trigger the recovery, so to reboot the network driver. However, in order to have a packet loss percentage of 0%, a packet loss of 0%, we are going to instantiate a shadow driver, which is going to receive requests, so buffer incoming requests from the different virtual machines and reply to them. And then when the network driver will be now ready to receive requests, it's going to send the request to the network driver for processing. So we prototyped this with Zen 4.10 and Linux kernel 5.0.8. And during evaluation, we were interested in the override we impose on virtual machines in terms of IO application, the reactivity to faults, and the repair and the fault repair times. So for the Zen Store UK, we impose an override of 20% on the virtual machine creation operation, which is the tax that heavily impose a load on the Zen Store, which is a degradation of up to 900 milliseconds, but it is better than the approach that consists of rebooting the different components, which is called ZOR, that impose up to 51% override, which corresponds to 2.3 seconds. So we are able to detect crash or data corruption 1.5 and 5.5 milliseconds after he has been triggered, and we are able to recover from a faulty replica in 25.5 milliseconds. And we are able to maintain read and write latencies to the Zen store at an acceptable rate, which is largely better than what is incurred by ZOR, which is up to 1,000 times more. However, we impose a higher overhead with high latencies, because with high latencies, we must ensure that each replica has to correctly apply the request before replying to the client. So for the net UK, we with all the heartbeat and timer mechanism, we impose an overhead of 12 to 17% for network applications inside virtual machine for their mean latencies. However, when the fault occurs and the fault is triggered by the network driver, we are able to detect it 25 milliseconds after the fault happening, and recover the network driver in our 4.7 seconds, which is just the reboot of the network driver, with a packet loss percentage of 0. And this is usually better than ZOR, that has a packet loss of around I don't know, here is 2 million, and even better than other techniques that try to propose a fault tolerance approach for this particular component. So overall, we propose PPVMM that relies on disaggregation, specialization, and proactivity. The prototype that was built shows that we can have acceptable detection and recovery times that are even better than state-of-the-art approaches. And in fault-free situation, we incur 12 to 17% overhead for virtual machine I/O applications. So to summarize, we're interested during my thesis in providing solution for the resource sizing, placement, and fault tolerance of the privileged virtual machine. So we have three main contributions: closer, I-flipping, the one for zero copy, and PPVMM. And the code source of all these solutions are available to the research community. So since no work is perfect, I think there are some improvement that can be done. First, with the zero copy solution, I think there can be workloads that will benefit more from the page pool or for the asynchronous memory migration. So I think I'm interested to propose a benchmark or a tool that will detect for each application what is the correct technique to use. For PPVMM, since there are a lot of timeouts, hard bits to configure, I think it would be interesting to propose an auto configuration or even some mechanism to, based on the Linux kernel or based on the kernel you are running, to configure this value for an optimal low fault tolerance system. I also think of combining the idea presented in Closer and PPVMM, since we have separated the privileged virtual machine into several components, and this component also needs sizing. So I think I'm interested to reuse the idea of Closer there for good sizing policies. Now, also long-term perspective, where I think the key idea presented in Closer, which is to execute as close as possible to the target virtual machines, and also have good sizing for each component, can be reused in other contexts, such as function as a service, where we have a lot of components that are going to be triggered by an event generator and going to schedule the event in order to trigger a function execution. I also think of clearly outlining, since I've worked in type 1 hypervisors, I think it's interesting to clearly outline the difference between type 1 and type 2 hypervisors to show really the advantages, to show the disadvantages, and when it is good to apply one compared to the other. This is mostly because I see a shift to KVM, so to type 2 hypervisor, mostly because there's Amazon that shifted from Zen to KVM because of the Linux community that stated that they're going to now only maintain the Linux KVM, and they will not more really take into account the Zen development. So I thank you for listening to my presentation, and if there are any questions, I'll be glad to receive them. Thanks.
So thank you very much. Merci beaucoup pour la présentation. Alors, on va commencer maintenant la série de questions. We'll start by the reporter from further away. I don't know if Willy is in Australia or in Europe, but Willy, please go ahead with questions. You can start.
Yeah, Willy is in Australia. I guess sort of my main question is that, you build these improvements on a system that actually is commonly used in production, and I'm sort of wondering whether you have thought about whether some of these ideas could be implemented in production systems, or whether you've tried it, or if there are things that would prevent the ideas from being implemented. Do you have any idea of that?
Yeah, I think implementing it in production environment is something that is envisioned. We have some contacts with some cloud providers such as Nutanix. However, I think implementing such solutions in a production environment must be, I think we must take into account other aspects, because here, if you see in most of my evaluations, I'm principally focused on performance improvement. I think what we introduce can also cause security issues, for example. So before trying to implement this, I think there may be some security audits that must be done with what we have performed, because all of our evaluation was mostly on performance. I think that is what can hinder the adoption of this current system in production environment. But yes, it is envisioned to do so, and it will be really great to try to have one of these approaches implemented in a real production environment.
Could you just give an idea of what one of these security issues would be, potentially?
I think it is maybe the let me think straight for tick 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 tick. Yeah, for example for PPVMM where we have the Zen store which we replicate on the same server, we introduce a component which is etcd. So we introduce a component in order to maintain synchronous state among all the replicas, and that component I think that component can be easily hacked and be used to reroute the request sent to the Zen store to, I don't know, to a malicious virtual machine or something like that.
Okay. Let me then maybe ask one more sort of low-level technical question, perhaps. When you do the second part, the sort of better implementation of memory flipping, essentially, does that have any effect at the application level? Does it affect the memory management? Is there like restrictions that you have to put on where you can do I/O or where you can? Because you're saying that the application cannot access those pages anymore, right? Because you don't want them to be remote.
Exactly.
But does that cause any restrictions then in the application?
The restriction, I think, is just the amount of memory the application will be able to use. Because what will happen concretely is that each time an application will do a malloc operation, for example, if it hits on the pages that are marked to be present in the pool, we are going to redo a malloc or send it to try to allocate pages which are not on the pool. So I don't. It's not a restriction, but it will increase maybe the memory page allocation time, and if and it is true, if there's a huge an intensive network application that is running in the virtual machine, I think that there can be a situation where the pool is going to, for the dynamic pool side, the pool can grow up to maybe reserving all most of the memory and cause a lot of page faults for other applications. So that is something that can be improved.
Okay, thanks. I'll pass back to Pascal.
Okay.
Ok, thank you. Merci. Donc, je vais en profiter pour poser quelques questions aussi, vu que je suis le rapporteur. You prefer English or French?
French, English, allons-y en français, c'est comme tu veux.
Well, okay, let's do English. That way
Okay.
we can understand everything.
Cool.
So, in the first part of your, by the way, and the presentation was also very good. Presentation. I have a question on the first part of on the first part of your thesis. So you mostly focus on I/O performance.
Exactly.
How does it translate to other kind of, for instance, the access to the disk I/O? Does it also provide you the same benefits?
Yeah.
Or is it because all of your benchmarks are based on network I/O?
Yeah. So maybe something I didn't present here because of time limits, but in the manuscript I present also evaluations for disk okay, nice, for disk IO for these applications. So there are also benefit from disk since because it is based on the same model. So you have the communication between the backend and the between the front end in a virtual machine and the backend in the privileged virtual machine that is going to perform the request and reply to the target to the virtual machine that send the request. So effectively, the work we did with Closer there's an improvement with disk IO, but here during the presentation I didn't present it, but in the manuscript I did show the improvement at disk level.
Okay. So I have a quick question regarding security. I mean, you mentioned that to discuss this a little bit with also with Willy.
Yeah.
So you are actually acting at a very low level of the hypervisor. Essentially, you need some control, some complete control over the system and the hypervisor. You essentially increase the size of the TCB. So there's also, of course, a security risk here. How much control do you need over the hypervisor and the VM itself for you to do the resource allocation? And the second side of the question that will answer in the second step. So assume that we want to use some techniques like SGX with really code that is running within enclaves, and you have encryption level memory. How would you? Would it work? Because at some point you need some intrusive mechanism going in the VM. You need to have control over the memory. So I'm wondering how this marries. First, whether you're introducing some security risk because you're increasing the size of TCB, and then whether you can also manage things that would already be hardened using other security techniques.
Yeah, for the first issue regarding the TCB of the hypervisor, most of our implementation didn't really improve the size of the hypervisor by much. I think we have some values that are presented in the manuscript. I think we increase, we just add, I don't know, maybe 500 line of code. So I don't think the size or what we introduce in the hypervisor is really large to consider it as a problem in terms of security. And for the second issue regarding if there are hardened mechanisms such as SGX that can hinder us from doing hacking the allocation, for hacking the memory allocation in virtual machines. Honestly, if for approaches for solutions such as the one with zero copy, if there is SGX involved, I don't know. It is clear that it will not be as easy as currently. Maybe we need to do encryption, decryption, communicate with the enclave at each time. I think the overhead of doing that for each allocation, I think the overhead will be so huge that it will even hinder the performance improvement that we want. So if we have mechanism as SGX, I think we need to rethink the functioning of our current design in order to take that into account and not shoot down all the improvement we could obtain from the solution we propose. Your mic.
Sorry, I was muting because there's some echo otherwise.
Okay.
So can you support also an environment where you have the number of vCPU is changing dynamically because you assume that you know it up front? There are systems in which you can change dynamically the number.
Yeah, just be sure because I didn't hear the start of the question. You're asking how our solution will behave in an environment where vCPUs can change dynamically.
Yeah, you're doing resource allocation, assuming a given number of vCPUs. So what if dynamically I change the number of vCPUs?
If you change dynamically the number of vCPUs for virtual machine, I don't think there will be a problem because what we do is each time we want to do allocation, that is mostly for the sizing part. So for the first part of the thesis, I guess. What will happen is that if the number of vCPU for virtual machine increases, we are just going to increase also the number of target CPUs where we can run it's not really related to the number of vCPUs of the virtual machine, but where those vCPUs are running, so on the number of physical CPUs on which they can run. So if we increase the size of the number of vCPUs, there will be no problem. It will just adjust itself with no intervention of us.
And still, one last question regarding resource allocation. Let's say have other objectives than just raw performance, and say, for instance, that you want to improve the packing of the VMs on some on a few machines in order to, for instance, lower the energy footprint of the system. It's something that could be added to your system.
So because I didn't, can you repeat the first part of your question, please? I didn't hear you well. Yeah, can you repeat the first part of the question?
Regarding resource allocation, because you are essentially working at the level of resource allocation. Can you have another objective? For instance, you might want, let's say, to do more efficient packing of the VMs on a few servers, just to save on energy, or to change a bit the metric.
Yeah. I'm not an expert in energy consumption, but the gain we are having is mostly in the privileged virtual machine size, so the memory and the CPUs where they are going to run. I don't know. I don't want to say some bullshit here. So I don't know if what we do, so the strict sizing of the privileged virtual machine is going really to save something in terms of energy consumption. That I can't really tell. But for packing issues, so if you want to increase the consolidation rate, this is effectively a use case, because since we are not going to over provision the resources for the privileged virtual machine, I think we can gain some space to run other virtual machines on the server. So regarding packing, that is nice, but for energy consumption, I don't want to say something about it because we didn't really perform some evaluations yeah.
Well, I'm mentioning packing because if you pack on several servers, you can typically turn off some other servers, and this is really a great saving in terms of energy.
Yeah, in that sense, effectively, yes. But I was more saying in the sense, on a physical server, you are kind of gaining, or you are kind of using less resources than previously. And I don't know if on one server the gain is really important in terms of energy.
Okay. Well, I have one last small question, because then otherwise I will take too much time. So the work you did with PVM resource management and zero copy, so you've identified some bottlenecks there, and you've found a very nice way of to just go avoiding and solving this bottleneck. I was wondering, how much is your solution Zen specific or hypervisor specific? Is it something that is really applies to any kind of type 1 hypervisor? And because it seems you're really getting into the technical implementation of Zen.
For the zero copy, it may not be implemented in the same way as Zen, but type 1 hypervisors that I know, that Hyper-V and other, use this split model architecture, where we have the privileged virtual machine with its component that we communicate with the target virtual machines, and on the other side there's effectively the zero copy on other hypervisors. So I think the solution, you just need to maybe to implement 2 or 3 line of code, but I think it can be re-implemented, it can be used on other hypervisors. This is not really something that is specific to the Zen hypervisor, so there will be no issue, I think. Yeah, there will be no issue.
So thank you. I'm done. I asked a lot of questions, so maybe I will turn back to Willy because he only asked 2 questions. Do you have some other questions, Willy, or you want you done and we go over the other members of the jury?
Let me just ask one more question. When you use a shadow driver,
Yeah.
you clearly lose some performance. Is that because you have to do 2 copies for every packet, or where does the loss in performance come from?
Yeah, the loss mainly comes, as you said, in the copy. So because you have to, because the shadow driver, either there's no fault, so it's just going to monitor all the packets that are going through the network driver. But when there's a fault, we need to copy all this and send the information back to the virtual machine. I think this copy is imposing a kind of latency that will hinder the performance.
Okay, thank you. Back to you, Pascal.
Excuse me. I go to the examiners. On va passer aux examinateurs. Alors, je les prends dans l'ordre. On va commencer par Daniel Agimon.
Okay, can you hear me?
Yeah.
Yeah, so it will be in English. First I would like to congratulate you. So I know you work a little bit because I was involved in some of your work. So I like seeing a PhD defense like that because it's an opportunity to see what you have done in the large. And if I take a step backward, I mean, one question. So I will have only one question because I know most of the things. My question is, I don't know, Job, do you remember a work that was done 25 years ago? I think it is exokernel. You know.
Sure.
So
Yeah.
you know exokernels, the idea of exokernel, because each time we are thinking about that, about architectures like that, I think we get back to that contribution, exokernel. In exokernels, the philosophy was to push the kernel in some library of OS, okay? And you could translate that in your context saying, I would like to push a part of the hypervisor in the virtual machine. You see, the same kind of idea.
Yeah.
And that means that the hypervisor would be there just to grant access to some resources, but most of the stuff which is done in the DOM0 would be done in a library hypervisor within the virtual machine. You see what I mean?
Yeah.
And that means that this is in some way what is doing hardware-assisted virtualization.
Exactly.
On that would be, but if you don't have that, that means that the DOM0 would receive interrupt, and it would only send the interrupt to the virtual machine, which would do the copy, which would be granted access to the hardware in order to get a copy of the data, for instance.
Yes.
So that you see what I mean?
Yeah.
And
Okay.
so my question is. Could you conclude that to have a PVM is a misimplementation? It's a mistake, and that a kind of exokernel-like design would be tracked to solve that problem more elegantly.
That's no, that's a hard question. Saying it's
You're planning to be a doctor.
yeah, saying it is a misimplementation, I think maybe a bit harsh to say that because maybe in the context where this architecture, so this split driver model was done, it was maybe, I don't know, it was a workaround to rapidly prototype something to propose and start benchmarking some solution. Because what you are trying to explain, it is really nice, but it is I think gvisor is trying to do something like that. So the hypervisor proposed by Google, having most of the library, what is done by the, most of the work that is done by the hypervisor being done in a library that is being exported in the target virtual machine. But the recent paper shows that doing so, if it's not currently implemented, I think it's a GVisor case study, something like that at ATC 2018, shows that doing so, you have up to 2 times overhead on the IO path. So I didn't clearly read the paper to see why there's that overhead. But I think people are thinking about what they are saying. People are even trying to implement that, and if it is not for the moment the dominant model, I think that there are reasons for that. So saying it is a misimplementation, I will not fully agree. Maybe it is a step to having what you are saying, and maybe with hardware improvements and maybe some hacking, what you are saying is going to be. But I think most hypervisors are trying to tend to what you are explaining, because if you see
the idea is to indeed less things in the DOM0.
Exactly.
You have only the thin layer that you need to forward
Yes.
this all the events to the virtual machine.
Yeah, so I think we are moving to that. If you see Firecracker proposed by Amazon, most of the work is done by the hardware. If you see other hypervisors proposed by other companies and other research laboratories, we are trying to move to that, but it's not, for the moment, it's not it, but it will come. So for the moment, let's work with the PVM.
Okay, thank you.
Alors, on va passer au second examinateur, Marc Chapiro. Tu nous entends, Marc? Alors, Marc, tu avais des problèmes de connexion tout à l'heure.
Oui.
Ah oui, c'est bon, ça va.
Donc, j'ai un petit peu de mal à suivre la discussion. Si vous entendez mal, dites-le moi et je couperai la caméra.
Ok.
Merci beaucoup, Djob, pour cette présentation. I prefer English, actually. So
Okay,
thank you
no
very
problem.
much for your presentation. You covered lots of ground. Maybe it was a little bit too fast sometimes. And I appreciated a lot your approach, where you motivate everything you do with benchmarks. I think that's a very, very important thing to do in systems. I have a few technical questions. So in your zero copy approach, your approach to solving the zero copy problem, you propose 2 different solutions. One is the memory pool, and the other is the asynchronous migration. And you don't seem, is there any good reason not to combine them together?
Yeah.
Why can't you have?
Yeah, at the moment, we thought of combining the two. I think it was mostly due to maybe technical reasons. We had the ideas, so I think the team was, okay, let's start implementing this solution. After, let's start implementing this. At the end, I think what we observe is that there may be some workloads that will benefit more from one technique than the other. I think we are moving forward to try to detect which is the best technique to use, and not trying to combine them. It is so that I haven't really thought about combining the two approaches. Maybe it is something that can be interesting to examine. So yeah, so honestly speaking, I haven't really tried to imagine if you can combine the two solutions. I think the idea was trying to see what is the technique that is better for one or this for this situation. But I think it can be interesting to see if you can combine the two. First, try to find the workloads that will kind of benefit from this fusion, and try to see if it is interesting to implement that. Your mic, please. Okay.
Could you go back to slide 39?
39. Okay. Yeah.
Well, maybe it's the next one. So exactly what do you mean by? I did not really understand what you mean by by this migration. So the pages that are inactive, which pages do you want to migrate? I didn't understand. You could migrate everything. What's asynchronous and what's the migration?
So the migration is done on the pages of the virtual machine that are remote. So we have pages. So the virtual machine is only on a particular Newman node at the start, and then with zero copy and all what is happening, there's some of its memory that is now remote. So what we just do is to asynchronously copy them or asynchronously put them back to where they were. I think.
But
Yeah.
what if they're actually in use at the moment where you migrate them?
Ah, yeah. If they're in use, we must wait. I think if they're in use, we must wait. I think one of the heuristic we were thinking of is so we want to do asynchronous migration. So when is the ideal time to migrate that? Is it when we observe that there is maybe less memory activity, and if because the solution we propose here periodic and based on the amount of remote memory, effectively if the page is in use, we are going to wait. So we need to wait that the page is free before copying it.
And what's the mechanism for waiting to know whether the page is in use?
We just look in the what will yeah just in the kernel to see this page is being currently locked by a process in the kernel. That is it.
Okay. Can you go down to the performance slide?
Uh, this one.
Yeah. So asynchronous migration, the dedicated page pool looks nice and it's quite flat,
Yeah.
which is a good thing. Whereas the migration, you see lots of variation.
Exactly.
Is there an explanation for that?
Yeah, because what happens is that this is periodic. So after a certain period, what we do, we are going to force the
Okay.
yeah.
Okay. Makes sense. Okay. My other questions was about the fault tolerance part.
Yeah.
Around slide 51.
Okay. 51.
So you mentioned that you make several replicas of this on this. You mentioned several times that it's on the same server.
Exactly.
So the same physical machine,
Yeah.
right? What's the point? I mean, if it's on the same physical machine, if there's a failure, they're all going to fail.
Yeah, I think maybe it was much just to explain to precise our fault model. Here we principally target the failure of the components of the privileged virtual machine. Here we consider the hypervisor to be safe. So we are not in a situation where the whole system will fall down. Maybe all the components of the privileged virtual machine can fall, but not to the whole system. So that is why we can permit ourselves to have the replicas on the same physical server. But yeah, if you are trying to target the fault model where so the entire system hypervisor and everything is going to crash, I think we must try to find a way to kind of store the replicas on other nodes that we serve for recovery.
But your motivation, you said you want to guard crashes, but you also want to guard against lack of resources. So if you're on the same server and if one of them lacks resources, the other one is likely to be lacking resources as well.
Yeah, but yeah, so what you are saying is that if you are in a situation, if the physical server we are lacks resources, That means that on the other servers, we are also going to lack resources. Is that what you're saying?
Yeah, yeah.
Yeah, I think if it happens, there's no. I don't know if everywhere there's no resource, we are stuck.
Right, but that was your motivation. You said you want to do replicate in case there's a lack of resources. So replication is not going to help you here.
No. What I said, maybe I said it wrongly, is that the Zenstore can be not replying if it is like, yeah. I think in the case of lack of resource on the physical server, this architecture will not help for the lack of resource problem.
Okay. And what do you do for slowdowns? I mean, if one of the replicas is very slow,
yeah,
how are you going to detect this with timeouts or what?
Not us. Not us. We are not doing it explicitly, but ETCD, since it is a component which is done to manage this kind of situation, is going to handle it. So it introduces some kind of components which are going to communicate constantly with him in order to say, okay, this replica is good, this replica is having good performance, and it will be based on that is going that it will choose the correct replica to send the request for processing. So I think if there's replica that is undergoing some slowdown for any reason, it will be handled at the level of ETCD.
I'm not convinced because that you're not taking into account the actual performance or response time of your components.
Because I what I know is that ETCD will take that into account. So sometimes it's going just to send some fake requests, some fake operation, to see what is the response time of each of the components that are linked to him. So that are linked to him. So he's going to be, yeah, I think ETCD is going to handle that for the response time of each component for each Zenstore. But
Okay.
it doesn't carry out any evaluation to back this up. So
okay. So let me ask a more general question, my final question. So you presented three different things, right?
yeah.
Three sort of so your contributions appear sort of disconnected. I mean, they're all, of course, they're all about virtual machine monitoring, but they seem sort of disconnected. So do you see a common theme, an sort of overarching direction?
Yes, because I think if we combine the fault tolerance solution with, because for the fault tolerance solution, we have several components, and for these components to perform correctly, they need to be correctly sized and the memory allocation should be correctly done. So we can combine the work on closer to do correct memory allocation. And for the network, components, so for the network submodule, we can use what we did at the second part at the level of zero copy for it to improve the performance of virtual machine. So I think the three, they might seem disconnected, but I think they can be fusion and build something which is a kind of a big system.
What is your future plans? Are you going to go into academia
Me?
or industry? Yes.
Academia. So I want to continue academia. So I will try that.
So you have to present a research plan.
Yeah.
So what is the title of your research plan for the future?
The perfect hypervisor. Honestly, the research plan. So I think presently is to kind of really, how should I say, to find the right architecture that is going to benefit from type 1 hypervisors advantages and type 2 hypervisors advantages. Try to fuse them and have a kind of ideal hypervisor that is going to perform correctly. That's something I'm thinking about sometimes when I'm working. So if I have to present a research work, I think that is the one I'm going to present.
Okay, thank you very much.
Okay, thank you. So now we move to the final examiner. Renaud Lachaise, at toi.
Yes, can you hear me? Yeah.
Perfectly.
Okay. So first of all, Job, thank you for the presentation and the document. So I had the chance to collaborate with you on some of your works, some of which are in the thesis, and some others which do not appear in the thesis. And actually, I also wanted to highlight that because you started your PhD studies less than 3 years ago, and you did many things that we have not been showing today. So I find this quite impressive. And yes, I just wanted to know, I guess your advisors will also have many nice things to say about you, so we'll keep it short, and I will give you a longer French version later today probably. But yeah, I wanted to say it's been a real pleasure to work with you. The technical level, scientific level, and also at the human level, right? So I really wanted to stress that. Okay, I would like to get back to some discussions you had previously with Daniel and also with Mark about hypervisor design. Okay, so you framed your PhD manuscript with the angle about PVM-based hypervisor designs, right? But as you mentioned in your conclusion, the landscape these days is starting to change a bit. Obviously, the PVM-based design are still fairly dominant, fairly mainstream, especially in production systems for reasons you outline in your document. But as you know, we are witnessing some, new proposals that are gaining traction. So, for example, even in the Xen context, now there is an alternative design which is DOM zero-less, mostly aimed at embedded systems, automotive market, and so on. But they're trying to push that thing. Also, you know that KVM is gaining traction, especially in the cloud, and so perhaps also because it allows the hypervisor to benefit from the latest advancement in scheduling, in observability, profiling subsystems, and so on.
Mm-hmm.
You follow me so far?
Yeah.
Okay. We also, as you mentioned, AWS, and now they have this co-designed hardware-software platform, the Nitro platform, which is KVM-based, but mostly relies on hardware assist and so on, in which they say they have gotten rid of the DOM zero that they were using with Xen in previous generations. And also we are seeing some progress with the support for live migration despite pass-through with SRIOV devices and so on. So my point, so obviously, just to be clear, I think your contributions are very useful and they will be useful for a couple of years, clearly. But how do you see this evolving? You mentioned the perfect hypervisor design. So what's your take on that? Do you think PVM-based designs will still be here in a couple of years, or maybe all their added value will have, disappear?
Okay, so difficult question. No, I think the previous virtual machine, even if it holds, is going to be reduced. I think will not completely disappear because even when we talk about the DOM zero-less that you're stating from Xen, there's still the DOM zero. So what they're just doing is that they are trying to making some critical application in embedded system that must start rapidly, not wait to the boot of the DOM zero. So, but after the boot, the DOM zero is still present there to handle some tasks. And even in the Nitro architecture with Amazon, there's still a kind of DOM zone. I'm not calling it like that, but there's still that component. So I think we are going to shift to design where there will be this control component, the privileged machine, that's going to do. I think it's going just to do monitoring. So it's just going to give you access to monitoring tasks in order to, I don't know, give you information about what is running. And most of the work will be done either by the hardware or even disaggregated components. But however, there are a lot of works that are proposed on this side, but there are also a lot of drawbacks because, as I stated with Daniel, Gvisor came and said, "Oh, we have a nice thing, this." After when evaluations result came, we saw it was not as nice as they stated. There's Intel that came with, I think it was Kata containers. Now I think it has a different name now. They proposed something similar where they stated there was no privileged virtual machine, but they have a kind of component that monitors. I think the calls that are done between the hypervisor and the virtual machine. After that, they had to completely redesign it, so they proposed a new version. I think the name changed. Kata container moved to maybe something else. So yeah, we are not still there to get totally rid of the privileged virtual machine. And even if the concept of privileged virtual machine goes, I think there will still be that monitoring component, and most of the work will be done in the hardware. So my guess is that the hypervisor of tomorrow will be just a kind of module that will perform scheduling, memory management tasks, and we have some components somewhere where you can access to obtain the information on your running virtual machine. So between the virtual machines and the hypervisor, there will be no there will be hardware, so there will be no component between the two, but there will still be that small guy there to perform monitoring tasks.
Okay. Do I have time for another question, Pascal?
Yeah, sure.
Okay. So in your conclusion, Djob, you also mentioned the fact that you intend perhaps to study how you could apply the ideas that you propose in the context of Closer to the context of fast platforms. Can you expand a bit on that?
Yes. In function as a service, for what I know, generally there's a kind of controller machine that will receive the request coming from the event generator, then send the request to kind of compute nodes in which we are going to run sandboxes, and in the sandboxes we are going to run the functions. But there's still this question of all these components, which resource we provide to them. Should we completely leave out an entire server for one component, or try to have a good sizing mechanism for either the compute nodes or even the whole controller or monitoring task? And also there's this what did I want to say? Yeah, there's these sandboxes that are created each time, but that using the memory that is given by the user, but the user is not going to use all the memory. So I think there's still this sizing issue. So how to correctly size, how to correctly place requests in order to benefit from locality, in order to benefit from in order to have a correct memory sizing. So when I said reuse the Closer idea, it was mostly in terms of the mindset of Closer. So Closer here, it means try to execute as close as possible to where it will be the best. Try to have the correct sizing for each component that is on your execution path. And I think in function as a service, this is not something that is being correctly, or that is being currently investigated, because we are mostly the papers I see are mostly in terms of the performance of the function that are going to run, the security of the function, but the components that trigger all this, there's really no work for the moment. No work that is doing the sizing of these intermediate components.
Okay, Okay. Perhaps the last question. Is that okay? Pascal? Okay. Okay. Then I'll put it to everyone. Okay, so I'll stop here. Thanks.
So then we just conclude with the two co-directors. So maybe Alain has something to say or to ask briefly.
Merci Pascal. J'ai pas de questions. Juste dire que bon, les soutenances comme ça à distance, ça commence déjà à bien faire. On aimerait bien avoir soutenance physique et avoir le pot après, mais bon, c'est pas grave. Donc, ça a été un plaisir de travailler avec Djob que j'ai récupéré, que j'ai eu au Cameroun d'abord comme étudiant à l'école polytechnique de Yaoundé. Et en fait, la rencontre avec Djob était particulière. On s'est d'abord rencontrés lors de... Il m'avait été proposé par des enseignants quand on organisait une école d'été. Et donc, il faisait partie des étudiants en 4e année qui transportaient les tables pour nous aider à faire les salles. Et ensuite, en M2, donc en 5e année, je l'ai eu en cours. Et après, donc, j'essaie tous les ans de proposer des stages aux étudiants. Donc, je leur laisse un projet et après, ceux qui réussissent bien le projet, j'essaie de trouver des financements pour les avoir en stage. Et donc, c'est comme ça que Djob a commencé en stage avec Daniel et moi à Toulouse. Et après, il a réussi à avoir un financement qu'on a continué avec Noël. Et j'ai trimballé Djob dans plusieurs villes. Donc, à la fois Toulouse, Nice, Lyon. Et bon, partout où il est passé, en plus de ses qualités, de ses compétences, ses qualités scientifiques. Et ce que beaucoup de gens ont remarqué, c'est ses qualités humaines. Donc, la capacité à s'intégrer dans toutes les équipes, que ce soit dans l'équipe ou même en dehors de l'équipe, le fait qu'il s'intéresse à tous les travaux. À chaque fois qu'il y a des réunions d'équipe, c'est lui le seul qui va poser des questions sur tous les autres travaux. Donc, ça montre son ouverture et ça, c'est très appréciable de travailler avec une personne comme ça qui est ouverte et qui est capable de discuter sur tous les sujets. Donc, c'était un plaisir, Djob, et merci encore pour ces bons moments qu'on m'a dit. Voilà, je vais passer la parole à Noël, au président du jury, pardon.
Qui va passer directement la parole à Noël. Donc, Noël, directeur de thèse, c'est à toi.
Je vais remettre ma vidéo. Eh bien, Alain a fait une éloge tout à fait méritée de Djob. Donc, je vais pas prendre beaucoup de temps. Je vais répéter peut-être un peu certains points. Enfin, en tout cas, Alain, Djob, pardon, merci pour toutes ces années de thèse que tu as passé avec nous. Et je soulignais aussi le travail acharné que tu as effectué avec une dernière année dans des conditions particulières pour tout le monde, avec le lockdown, le confinement. Et tu as traité un sujet difficile avec brio et une certaine facilité, quoi, comme si c'était comme si c'était des choses faciles, quoi. Donc, tu as toujours été volontaire et puis moteur dans les recherches. Donc, comme l'a dit Alain, tu as fait une bonne moitié de la France, quoi. Enfin, tu es passé par Toulouse, Nice, Grenoble, Lyon, etc. Tu n'as jamais rechigné, quoi, à ça. Donc, et cette mobilité, ça t'a formé à cette richesse de la mobilité avec, du coup, bon, là, il y a moi et Alain, mais au final, le panel de personnes avec qui tu as interagi et qui ont aussi aidé et qui ont donné aussi leur avis sur le travail a été beaucoup plus large que juste moi et Alain, quoi. Et pour finir, ton parcours depuis le début a vraiment été remarquable, quoi. Donc, chapeau bas pour tout ça. Et puis, je terminerai par deux choses. Déjà, je suis fier d'avoir été un de tes directeurs de thèse. Et le deuxième point, je voulais remercier aussi Alain, quoi, par qui, du coup, j'ai pu participer à cette thèse. Donc, Alain qui a été toujours en première ligne, et puis bon, qui du coup a fait aussi une grosse partie du travail d'encadrement, avec beaucoup plus de disponibilité que moi. Voilà, donc du coup, merci à toi, Djob, vraiment. Et puis merci à Alain. Et encore une fois, chapeau bas, quoi. Voilà.
Merci.
Merci beaucoup. Donc, cela conclut la discussion, la partie des questions. Alors, on va maintenant se retirer. Le jury va se retirer pour délibérer. Et on va reprendre, je pense, d'ici 20 minutes pour venir ensuite annoncer les résultats.
D'accord.
Donc, les membres du jury doivent normalement tous avoir reçu un lien pour aller dans un autre serveur, une autre chambre. Alors, on va se déplacer, puis on reviendra tout à l'heure.
Ok.
So Willie, did you receive the email or you have the link?
The
Yes,
meeting
I have
hasn't
the
started.
link. Yeah.
You have to start the meeting then. Est-ce qu'on peut rester dans les deux ou est-ce qu'on doit quitter l'un des deux?
Je pense qu'il faut quitter.
Ouais, si tu restes ici, si tu restes entendre sur YouTube.
D'accord, je quitte, on quitte celui-là puis on reviendra sur celui-là après.
Oui.
Comment est-ce qu'on quitte? Leave.
En haut à droite, il y a un menu normalement pour quitter. On the top right corner.
Oh, juste fermer la fenêtre, c'est
efficace. Dis donc, putain, mais... ouais. Bon, j'attends. Je vais aller prendre un yaourt là, parce que là...